Hi, I'm Tammy Lester-Clare from Portland State University. In this mini lecture, I'll describe how X-ray fluorescence instruments work by describing each of their components. By the end of this lecture, you should be able to understand how the instrument generates X-rays, how the energies of secondary X-rays from your sample are measured, and to gain a basic understanding of different instrumental parameters that can be tweaked to optimize sensitivity for certain elements of interest. Let's jump right in. This figure shows what is called a block diagram. It is a useful way to show how the components of an instrument are arranged. We will use this block diagram as a template and will elaborate on each of the 5 components for XRF. Let's begin by describing the source of X-rays. How do we generate X-rays? A high voltage is applied to the tungsten filament, which causes electrons to boil off. Those electrons accelerate toward the positively charged target metal. When the electrons crash into the target, they eject electrons from the atoms within the target. The rapid deceleration of those electrons as they ricochet within the atoms in the target causes their kinetic energy to be converted into X-ray photons. This type of X-ray emission is called Bremsstrahlung, from the German word bremsen, to break, and Strahlung, meaning radiation, so breaking or slowing radiation. Another thing can happen too. Sometimes those incoming electrons score a direct hit on an electron within an atom in the target metal, ejecting the electron from the atom. And we know what happens when electrons get ejected. Higher energy electrons within the same atom relax to fill the vacancy, giving off their excess energy as X-ray photons. Those X-ray photons emit through a window that doesn't absorb their energy, beryllium, and that's how we shine X-rays on our sample. Here, it's a bit heavy, here is an actual tungsten X-ray tube. Contained within this metal housing is the tube itself. When connected to the instrument, X-rays would shine out from this port. So what does the emission from that X-ray tube look like? So first, there are the characteristic emission lines from the metal target. In this case, the metal target was tungsten, and you can see the K alpha and K beta peaks from tungsten itself. And you'll also notice the broad curving background emission, the Bremsstrahlung radiation. Increasing the tube voltage allows you to select which emission lines you want to excite. Higher voltages allow you to detect higher energy emission lines. Here you can see the emission for 100 kilovolts applied between the tungsten cathode and the target itself. And you can see that that higher voltage causes higher photon energy. At a lower tube voltage, the emission energy of the Bremsstrahlung is lower. So depending on the elements you want to detect, you may have more than one X-ray tube. These characteristic lines will differ depending on what your metal anode material is. Incoming X-rays will most efficiently eject an electron if their energy is equal to or slightly greater than the element of interest. So elements having emission lines just to the left of tungsten's emission lines and at the height of the Bremsstrahlung will emit X-rays with higher efficiency than those further to the left or further to the right. For that reason, it is preferable to use X-ray instruments that allow you to interchange the type of X-ray tube, which allows you to select which elements in your sample are most efficiently excited. And that depends on the characteristic energy of the type of the metal target. Emission lines having energies greater than tungsten's emission profile will not be observed at all. Sometimes we need to detect trace amounts of an element. To do that, we can adjust the instrument settings to optimize for better sensitivity to certain emission lines. For example, we might want to select just tungsten's K-alpha peak to interact with our sample. By selecting the right type of filter, we can block the K-beta peak and allow the K-alpha peak to pass. That is the purpose of wavelength selectors, the second component of our block diagram, to select which energies are allowed to pass and which are blocked. In the blue trace is the emission spectrum from a molybdenum target X-ray tube. You can see the K-alpha and K-beta peaks for molybdenum. The black trace shows the absorption spectrum for zirconium. Notice that zirconium has an absorption edge that lies right between molybdenum's K-alpha and K-beta peaks. By placing a zirconium filter between the X-ray tube and the sample, we can block molybdenum's K-alpha peak from interacting with the sample. So with this zirconium filter in place, the actual energy profile of X-rays interacting with the sample are shown by the red dashed line. So in effect, we are simply allowing the K-alpha peak to be emitted and everything that lies under this black curve to be blocked. There are filters available to detect certain specific elements with high sensitivity. So if you know that you want to gain information about just one element, using a filter to permit X-rays having an energy just greater than the emission energies of your element of interest is recommended. Otherwise, if you want to know the identity of as many elements as possible within your sample, no filter is needed. These are actual filters used in a portable X-ray fluorescence instrument. They're pretty simple. They're just metal sheets glued onto an aluminum holder. There's the back side where you can see the metal sheet and the window showing the metal sheet itself. And you can make your own filters to suit your own specific application. And these are some commercially available filters for different elements with different sensitivity. Here are two XRF spectra taken with different filters. Using the blue filter and a lower X-ray tube voltage of 20 kiloelectron volts, we can observe greater intensity emission lines having energies less than 15 keV. So you can see in the bottom panel, we can see intense emission lines for the blue filter settings. Here's another view of the same data. In the bottom graph, I've expanded the energy range between 2 and 7 kiloelectron volts. So now we can better see the difference between the two filters and settings. Notice the peaks for calcium, chromium, and iron are visible under the blue filter settings. Those peaks are not visible with the red filter and instrument settings. Using the red filter, which contains copper, we can dramatically reduce the height of the copper peak that is observed. Filtering out the most intense peak in the spectrum can be a useful strategy to allow you to detect other peaks of interest in the spectrum. And here, with the red filter in place, the background is reduced. So the background level is greatly reduced. And peaks having energies greater than 15 keV have a greater intensity under the blue filter settings. With the red filter, we can confidently say that strontium is present, seeing both the K-alpha and K-beta peaks present in the spectrum. We can also detect silver, Ag, at about 22 keV. The third component of our block diagram is the sample itself. XRF analyses can be done in situ, meaning in place, such as on a painting, even within a gallery or an archaeological site. Alternatively, XRF analyses can be done ex situ, meaning that representative samples are taken and analyzed. Samples for X-ray fluorescence can be solids, powders, and liquids. Such samples can be contained in plastic containers with a thin plastic film across one end. Plastic is made out of hydrocarbons, which of course contain hydrogen and carbon, so their X-ray energies are too low to be detected when conducting analysis in the air. Samples for spot analyses should be homogeneous, well mixed, and contain fine grains, if reproducible spectra are desired. The working distance, which is the distance between the sample and detector, is less than a centimeter. XRF instruments are often mounted on a tripod to keep them steady while spectra are being collected. The next component is the detector. Detectors are the component that measures the energy of emitted secondary X-rays. Most portable X-ray fluorescence instruments use silicon drift detectors, or SDDs. Silicon drift detectors measure the energy of incoming X-rays by the amount of ionization they produce in the detector material. The more ions that are produced means that a higher energy X-ray hit the detector. A key parameter is the operating speed. Detectors need to be able to count how many ions were produced by one X-ray before the next X-ray hits the detector. Typically, SDDs can count in a time span of a millionth of a second or 1 microsecond. When an incoming X-ray hits the detector material to create ions, electrons are ejected in that process. And being negatively charged, electrons can be collected by their attraction towards a positive charge. So by controlling the charge of the concentric rings within the silicon drift detector, electrons are dragged and collected toward the center anode. The movement of electrons produces a measurable current, which is measured and correlated to the number of electrons that were ejected by the X-ray, which is a reflection of the energy of that X-ray. The energy resolution of SDDs is about 0.12 kiloelectron volts, which means that energy lines separated by less than 0.12 kiloelectron volts cannot be distinguished. For that reason, some of the alpha sub 1 and alpha sub 2 emission peaks appear as a single peak. The last part of the block diagram is the signal processor and readout. This is a portion of the instrument that receives electrical information from the detector and converts it into a digital form that displays a spectrum on the computer. This cartoon illustration shows the inside of a typical portable X-ray fluorescence instrument. Now, the 5 blocks of the diagram are numbered and arranged in a clockwise order. We have 1, the X-ray source, 2, the location of the filter, if one is used, 3, the sample, 4, the SDD detector, and 5, the signal processor and readout. I'll show you an actual portable X-ray instrument. Here it is. So the detector, or the source, is located here, and the detector is located here. Let me hold it exactly like the picture is showing. Okay. Here's the source back here, and the detector back here. And this brass ring on the side, this brass nut, can be removed and a filter placed into the instrument through that port. There are many online sources for more information about X-ray fluorescence spectroscopy, and so these are a few that might be most useful for cultural heritage applications and to gain a basic overview of the technique. Bye for now.